Hi. When we talked about equivalent exposures, we talked about them in terms of the shutter speed and the effect that changing the shutter speed would have on the image. Uh, we didn't talk about the effect of changing the aperture, and that's what I want to talk about now. And so when we change the aperture, aside from changing the amount of light entering the camera, we change something called the depth of field. And as you can see here on the screen, the depth of field is the area or the amount of space in the frame that is in focus. Specifically, it's the amount of space in front of and behind the point of focus that's in focus. So if you focus on my nose, there's always a certain amount of space in front of my nose and behind my nose that is also in focus. And that amount of space can be really small, or it can be expanded to be really, really big. But that space, that distance or area, is called the depth of field. And we can change that in an image by changing certain things. The ratio of that space is a constant. So of the total amount of space that is in focus, whether it be a foot or 2 feet or 10 feet or 100 feet, a third of the total amount of space is in front of the point of focus, my nose, and 2/3 behind. So I've drawn a little diagram here with my stick figures, and there's a photographer and the subject with other things in the frame. And so when the photographer focuses on the subject, a certain amount of space in front of and behind that subject will be in focus. So if you have, let's say, 3 feet in focus, then one of those feet will be in front of the point of focus and 2 behind. The ratio is 1 to 2, or 1/3 to 2/3. And it doesn't matter really how many feet you have in focus or how much space. That ratio is the same. So if you have a total of 150 feet in focus, 50 of those feet will be in front and 100 behind. Again, the ratio remaining the same. So as I said, the first thing that affects depth of field is the size of the aperture being located in your lens. And the rule is the larger the aperture, and that is the smaller the f-stop number, the shallower the depth of field, and the smaller the aperture, which is the larger the f-stop number, the greater the depth of field will be. So we see the world, generally speaking, in great depth of field, and that means where most or everything is in focus from the foreground to the background. Shallow depth of field is when very little is in focus except for what you've focused on. So, as I said, we see the world, generally speaking, in great depth of field. And our eyes contain lenses and apertures in the same way a camera does. And our aperture is the size of the pupil. And generally speaking, our pupils are relatively small, except when it's very dark. And then we can't see that much regardless. So I want you to do a little exercise with me. It's harder to do it on the computer and on Zoom rather than in person with me in front of you, but let's give it a try. So we all have a dominant hand, or almost all of us do. Most of us are right-handed, some of us are left-handed. A few of us are ambidextrous. But we also have a dominant eye. Usually, but not always, the dominant eye corresponds with the dominant hand. So if you're right-handed, your right eye is dominant. If you're left-handed, your left hand is dominant. Your left eye is dominant. Sometimes there's crossing over, and that's fine. How do you know which eye is dominant? That's the one that you look through your camera with. So the one that you don't close. So my right eye is dominant. I'm primarily right-handed, and I look through my camera with my right eye and I squint my left one. And it's not that I can't do it with the other one, but it doesn't feel right. So what you're going to do is figure out what your dominant eye is and close or cover, pardon me, your other eye with your hand and take your index finger and bring it as close to your eye as you can while keeping the finger in focus. And so for those of us who are older, our point of focus moves back and away from us as we become more farsighted. So for you young folk, you'll probably be around here. But what I want you to do is hold it as close to your eye as possible while keeping it in focus, and then look at the background. So you need to be in a place where there's some space. Probably you can look over your computer to something beyond it. So I'm doing that, and when I look at the background, my finger falls out of focus. When I look at my finger, when I focus on my finger, the background falls out of focus. That's what you should be seeing. So we have fooled our brains into seeing in a way we don't normally see, and that is in shallow depth of field, where very little aside from what we've focused on is in focus. And we did that by covering one eye and removing our sense of depth. Okay, so generally, again, we see in great depth of field where we do have the foreground and the background in focus. So now that you've done that, there's a second part to this exercise. You're going to take the hand that covered your non-dominant eye, and you're going to make a little hole with your finger, like so, kind of, and cover. You're going to squint and then cover your dominant eye with this hole so that it's really small. So if you're like this, that's too big. You need to make it really small. Do this, and then do the same thing, bringing your finger as close to your eye as possible while still keeping it in focus. And now you should see both your finger and the background in focus or sharp. So now, even though we recreated the situation where we can't see great depth of field, where we've removed our stereo vision, by using this tiny little hole or aperture, we are now again able to see in great depth of field. So that tells us that a small aperture, little hole, will produce great depth of field, where most or everything from the foreground to the background in your frame is in focus. So if we look at our notes here again, the first of three things that affects depth of field is the aperture, the size of the aperture. And so the smaller the aperture, for example, f/22, the greater the depth of field, the more space will be in focus. And the larger the aperture, which is a smaller f-stop number, for example, f2, the shallower the depth of field will be. That is, less will be in focus in front of and behind your point of focus. So again, that is the first of three things that affect depth of field, and I will record the next two so you don't have to watch it all in one go. All right. A continuation of aperture's effect on depth of field, and that is why this happens. So if we look at the camera from the side, or above, but from the side, we have the camera body and the lens, and then here a subject and some other information, some other objects in the frame. And when we photograph, the light from whatever we're photographing enters the camera through the lens, is focused by the lens, and then is transmitted back into the camera where it's recorded either with film or with a digital sensor. The light that enters the camera is the reflected light, and that's what we see, and light reflected by other objects, all objects. And so the light from the object on which we focused is focused at a certain point within the lens, and that point is called the nodal point, and it's the optical center of the lens. But of course, other light from other areas in the frame also enters the camera. So the light from this flower, the light from the building behind, unless your subject is in complete darkness, other light will enter. And though the light from those areas focuses at different points than the light from your point of focus. And so they create these little circles. They're called circles of confusion, which I think is a great name. But those circles of confusion are at different distances from the point of focus. But as you close down the aperture, that light is kind of bundled together. It's forced through this smaller and, decreasing aperture. And as you decrease the size of the aperture, those circles of confusion are forced to move closer and closer and closer to the actual point of focus at the nodal point in the lens. And so the light from these other areas is focused at this point much closer to the actual point of focus, and so those areas also appear to be in focus. They never quite reach that actual point, but they appear to be in focus. Then as you open up the aperture again, the light goes like, oh, thank God. Anyway, it separates again, and those points of focus, the circles of confusion, again move away from each other and away from the point of focus. The second thing that affects depth of field is the focal length of the lens, so how long or short your lens is. And the general rule is the shorter the lens, or the more wide angle the lens, the greater the depth of field, and the longer the lens, or the more telephoto the lens, the shallower the depth of field will be. Technically, that's if you compare two lenses together, but that is the general rule. But if we take two lenses and compare them, we will find that although these lenses have the f-stops in common, so for example, essentially all lenses have f8, f11, f16, but the actual diameter of that f-stop is not the same from lens to lens. So let's say we have one lens that's 24 millimeters in length, so that's a wide angle lens, and another at 80 millimeters, which is mildly telephoto, and we set them both to f8. The depth of field that we get from an image made on those lenses, from images made on those lenses at f8, will not be the same. So the diameter of the aperture is equal to the focal length of the lens divided by the f-stop number. Don't worry, this is not a math class. But if we take the 24 millimeter lens, which is the focal length, and divide it by 8, which is the f-stop, we get 3, and the answer is described in millimeters. And so the diameter of the aperture at f8 on a 24 millimeter lens is 3 millimeters. We then take the 80 millimeter lens and divide that by the f-stop number, 8, and we get 10 millimeters. So 80 divided by 8 is 10 millimeters. And so the diameter of f8 on the 80 millimeter lens is much, much larger than the diameter of f8 is on the 24 millimeter lens, on the shorter lens. And we know that the smaller the aperture, the greater the depth of field, and the larger the aperture, the shallower the depth of field. And so that's why a shorter lens will give greater depth of field than a longer lens will. Because even though in this case both are set to f8, f8 on the short lens is much smaller than f8 is on the longer lens. And so f8 on the shorter lens will give us greater depth of field than f8 on the 80 millimeter lens will. Okay, and so I've written here what I just said. Okay, and this information again is in the notes, in the class notes, in the modules on Canvas. The third and final thing that affects depth of field is the distance from the point of focus, or your subject. And the general rule is the further you are from your subject, the greater will be the depth of field. And the closer you are to your subject, the shallower the depth of field. That's the rule. The reason is due to the angle of the light. So when you're further away from a subject, the angle of the light entering the camera is pretty small. And it's easy for the lens to focus when the angle is small. But as you get closer, that angle increases and increases and increases, and it's much more difficult for the lens to focus when you come in close and that angle is greater. So you may have noticed that your lenses will not focus beyond a certain point as you come in closer. And the longer the lens, the further away from your subject you'll have to be. There are certain lenses that do allow you to come in very close. They're called macro lenses and micro lenses, and they're kind of specialty lenses and very nice to have. But in general, about 18 inches is the closest you can come into your subject with a normal lens. And beyond that, the lens just can't focus at those great lenses. And so when you have a subject that close, you can say it's kind of like all the lens can do to focus on that one point, and the lens just is not capable of showing other points in focus as well, so showing greater depth of field. But as you move away from your subject, as you back up, and that angle decreases, this angle that you can see right here in my wonderful drawing, as that angle decreases, the lens is more able to focus not just on the point of focus, but on areas, or include areas in front of and behind that point of focus. So again, distance from the subject or from the point of focus is the third thing that affects depth of field. So again, depth of field is the amount of space or the area in the image that is in focus. There are three things that affect depth of field: the size of the aperture, the focal length of the lens, and the distance from your point of focus or your subject. As photographers, when we purposely want to change the depth of field, it's generally the size of the aperture that we will choose to use. Because when you change the size of the aperture, you don't change your viewpoint. You don't change the composition of your image in terms of what is included and what is not. But when you change the size of the lens, the length of the lens, and when you change your distance from the point of focus, you do change the amount of information in the frame. So if you come in very close to me, you may just get my face. Whereas when you back up, you get a lot more information in the frame. And the same thing happens when you change the focal length of the lens. If you're using a wide angle lens, you'll get a lot of information in the frame. If you're using a telephoto lens, you get very little. You might just isolate my nose, for example. So again, changing the focal length of the lens, changing the distance from the point of focus, will change the composition of your image, whereas changing the size of the aperture will not. It will change the depth of field, but it won't change the composition. Now, of course, when you change the size of the aperture, you have to employ your equivalent exposures and also change the shutter speed. So if you use a small aperture to achieve great depth of field, you've decreased the amount of light entering the camera through the aperture, so you'll want to increase the amount of light entering the camera through the shutter. So we tend to have longer exposures with small apertures. So for example, you may see an image where the depth of field is very great, but if there's a moving subject in the frame, that subject is blurry because a longer shutter speed was used. In a situation where you're using a large aperture, for example f2, you'll get shallow depth of field, and you're letting a lot of light in into the camera through the aperture, and so you'll compensate for that by letting much less light into the camera through the shutter. So in that case, you'll have an image that has shallow depth of field, but if there's anything moving in the frame, that motion will be frozen or stopped, like so. So if you look at sports photography, for example, you'll notice that a lot of those images have shallow depth of field, just the subject is in focus, and the motion has been frozen or stopped. Now, that's not to say that there aren't sports images, and we'll look at them in my next lecture, but it's not to say that there aren't sports images that show motion, but a lot of them do stop motion. Okay.